Okay, so for FRQ4, there's a couple different ways you could do it, and depending on what you say for A, that might actually change the answer for B. So basically, this is really similar to the lab that we did, except instead of looking at just one bounce, we've got this rubber band. So the couple ways you could do it is you could, move the cart to the left and let the rubber band relax and push it, and look how the cart will slow down, maybe even reverse directions and come back. And you could look at the final and initial velocities at 2 times and find the area of the force versus time graph in between those 2 times. And that would give you the impulse, and you could find the mass kind of like that. Or you could just pull the cart back and let it go and look at the rubber band accelerating it and look at that interval. And that would be fine too. I'm gonna go with the second option, but either is okay if you explain it well. So for A, so what I would encourage, or the way that I would do it is I would say, and I'm not gonna write out the whole thing because I'm explaining it out loud, I'm making a video, right? I would say you pull it back, so you stretch out that rubber band, and then you release it. And it doesn't really matter how long you let it go for, but let's say you let it go until the rubber band becomes loose, right? So that way it's moving this way with some fast speed. Here it starts from rest. And over that interval, you measure the velocity, right? So you get a velocity versus time graph, position versus time graph, and you also get a force versus time graph. So here you would have to use the force versus time graph, and you would have to find the area, and the area would give you impulse. And the force is not going to be constant, right? So if you just said multiply force times time, that's not going to be correct because the force is going to change as this unstretches. Remember, Hooke's law says that the force will be greatest when the rubber band is most stretched, like a spring, right? It's elastic. And as it becomes less stretched, there will be less force, right? Because there's 0 force when it's relaxed, and there's a lot of force when it's tight. So you would have to use the area of the force versus time graph to get impulse, and then you would have to use either the position versus time graph or the velocity versus time graph to find the final velocity. The initial velocity is 0 here, so maybe if you were using the position versus time graph, and I'm not exactly sure what kind of curve this would be. It would definitely be speeding up the whole time, but I don't think it doesn't have constant acceleration because the force decreases, but it's still accelerating. So it'd probably be curved. Well, it would be curved, but it's not going to be a quadratic, but nonetheless, right, you could still find whatever this time is here. You could use, your fit tool and find the final velocity there. Or you could look at just the velocity versus time graph to get the final velocity, right? So there's a couple ways you could do it. And then you would basically just need to take this equation and take the impulse, right? So the area of that graph, and set that equal to m times delta v. And delta v will be the final velocity that you get using the motion detector data minus the initial velocity. The way I set it up, that would be 0. And then you could solve for m. So that's basically it for A, right? You don't really have to talk about doing multiple trials or anything like that, right? Nothing here says that you have to do multiple trials. So it doesn't have to be as complicated as the lab that we did on this. It's not like bad if you did, except for it might have just taken a long time to explain. Okay, for B, after gathering data, the students realized that the track was accidentally positioned on a slight incline. So let's just imagine if the track is inclined, how this is going to affect our results. Right, so if this track is inclined, and this is really exaggerated, but let's just think about it. Right, so if the track is inclined, that is going to slow down the cart. So if we think about our equation here, right, if the cart is slowed down, well, that's not going to change the force versus time graph, right? But what it is going to do is it is going to artificially decrease our velocity, which will make the cart look even heavier. So our M value, right, our experimental M value, M experimental value that we get from our data will become greater than the actual value. I wonder if there's another way we could think about this. No, I think that is probably the best way to think about it, right? Because the cart will move slower than it should under the influence of that rubber band force. And if the cart moves slower than it should, then it will look like it's heavier than it actually is, according to our data. But I mean, if you had set up the experiment differently, right? Like if you pushed it away and you looked at the slowdown, right? Then it would actually look like the cart would actually, you know, it would take longer to come to a stop if you had started it here and you pushed it down, right? And that would actually, I think, have the opposite result. I might need to think about it a little more carefully. But yeah, I hope this was helpful. And yeah, I'm glad to have, you know, had the opportunity to go through these questions. And if people were struggling with any of these concepts, I hope that this is going to be useful in preparing for your reassessments.